Hi, in this video I'm going to be looking at centre of mass and tilting, still both to do with moments. So if a rod is non-uniform this time, the centre of mass will not necessarily be at the midpoint of the rod. So we need to solve problems to consider the moment due to the weight of a non-uniform rod and the position of the centre of mass. So if we don't know those things, that's where we'll have to do some problem solving. So if we get straight into an example, you're going to see similar methods and techniques to what we're using with the equilibrium section. And there'll only be a few tweaks considering a different centre of mass now or a tilting aspect, which we'll see a little later on. So it says Sam and Tamsin are sitting on a non-uniform plank. So straight away, I know now that mass is not necessarily at the midpoint. The mass of it is 25 kilograms, but I need to work out where that is. And we're at length 4 now. I can see the 4 meters there. The plank is pivoted at M, so I can see there's a support here. Like a seesaw, it's going to pivot around M. The midpoint is, well, that's the midpoint of AB. Then the centre of mass of AB is at C. So I know where the centre of mass is. So I'm going to add that onto my diagram now. So there is the centre of mass, and that's going to be 25 G, gravity. And we can see that AC is 1.8. And then Sam has a mass of 35 kilograms, Tamsin has a mass of 25 kilograms, and she's sat at A. So I'm going to do a force here, a weight force of 25 G, and then a weight force here of 35 G. So this is Tamsin, and this is Sam. I'm going to add a few more things onto my diagram. So there's going to be a reaction force here. And I'm going to add on the distances. So if M, the pivot, is the midpoint of the plank, then if this is 1.8, that'll be 0.2. And then here, now I'm going to see about the distance from the midpoint, the pivot. So how far Sam must sit for the plank to be horizontal. That's what it's asking me for. So where must Sam sit for the plank to be horizontal? So I'm going to call that distance X. That looks like what we're trying to find. Now, if you remember, horizontal means equilibrium. So upward forces must equal downward forces, any left or right forces must be equal, and then clockwise moments must equal anti-clockwise moments. So I'm going to look at taking moments about M, okay, the pivot point. I could look at taking forces first, looking at the resultant force, comparing the forces, the upward and the downward forces. I could find R then, but because I'm taking moments about M, R is going to be eliminated anyway because there's no perpendicular distance to that force there. Other students might have thought maybe to take moments about maybe B and think about the distance Sam has to sit from B. That will be possible, but you'll have to include R then, which, yes, you can find it. So there's different methods sometimes, some more effective than others. So yes, if you were stuck, you can try taking forces first, looking at forces, then taking moments. I'm going to start by looking at moments, and in particular moments about M. So if I look at the forces I've got, I'm going to have a moment here in a clockwise direction, so that's the weight of Sam. I'm going to have a moment here from the centre of mass, and that's going to pivot the plank in an anti-clockwise direction, and then I'll also have Tamsin's weight causing the plank to pivot in an anti-clockwise direction. And if you can remember, with equilibrium, I'm going to set up my anti-clockwise moments equal to my clockwise moments, or vice versa. So I'll take Tamsin's weight first. Tamsin's weight, the force, times by the perpendicular distance. Now that's 2 meters all the way to M. So 25g times by 2. Then I will have the centre of mass force, so it'll be 25g also, times by that tiny perpendicular distance there. And that's going to be equal to 35g, Sam's weight, times by the distance he is sat from M, so x. Now I can simplify these on the left. I could add the 50g and the 5g together. And then I could divide by 35g. Now the g's will cancel, and I'm left with 55 over 35, which is 11/7, and I'll get that as a decimal. So that must mean that Sam needs to sit 1.57 meters from M. Okay? .57 meters from M, and I need to put from M because we could have specified from B. It didn't ask us in the question. Now, just to be clear, I didn't actually need to put the gravity in because the gravity was going to cancel. So watch out for that, because sometimes you can simplify it first without putting gravity in. So treat it like an algebraic equation. You could have divided through by gravity as well. So at this point you could have divided everything through by gravity, or even by 5g, and see what you got that way. Let's move on to another example. So a non-uniform rod, so again I'm thinking what that means. AB is 3 meters long and has weight 20 newtons. It is in a horizontal position, resting on supports at points C and D. So I'm going to draw those as supports. AC is 1 meter, AD is 2.5 meter. The magnitude of the reaction at C is 3 times the magnitude of the reaction of D. Find the distance of the centre of mass of the rod from A. So there's quite a lot going on, and of course there's no diagram, so I'm going to get to draw a diagram now. So I'm going to draw quite a long straight line, as straight as I can get it. So this is A, this is B. Now that's 3 meters long. Now it's non-uniform, So I don't know currently where to put the weight. So I'll hold on there for a moment. It's got support C and D. Now AC is 1 metre, so if it's 3 metres in total, that's about 1.5 there. So maybe it's there. So C. AD is 2.5. So again, if that's 1.5, add another 1 on 2.5. About there. Okay, I'm going to go a little bit shorter for that one. So that's 1 metre, that's 0.5 metres, because if the total to there is 2.5, the rod is 3 metres. And I'm going to have reactions on here as well. And it did say the magnitude of the reaction at C is 3 times the magnitude of the reaction at D. So RC is 3 times the reaction at D. I'm just going to put the mass then here. It's non-uniform, so not necessarily in the centre. So I'm going to say that is, now it's given me a weight of 20 newtons, so I will be leaving it as 20 newtons. So I'm trying to find what this length is here. Okay, the distance of the centre of mass from rod A. So what is that? I could add on some extra parts here. So if that is 1 metre to there from A to C, then from C to D, that must be 1.5 metres, okay, from there to there. So not massively to scale that, but I think you get the gist. Right, so remember, it's saying that this rod is in a horizontal position. So again, we're thinking about equilibrium here. And if you're ever unsure with these questions, just give something a go. So remember, I always say, if you want, have a go at finding forces and then have a go at taking moments. So I'll do that now. I'll have a look at forces. So if I resolve upwards, up is going to be down, or vice versa. So I'll have RC, the reaction at C, plus the reaction at D equals 20 newtons. Now I could use this relationship here between the reactions. So RC is 3 times the magnitude of the reaction at D. So I'm going to change RC for 3 RD. So 4 RD. So therefore RD is going to be 5 newtons. And if I've got RD as 5 newtons, well, RC is 3 RD, which equals 15 newtons. And that definitely makes sense, because then both of the reaction forces add up to give 20. I could have just put 5 in here to get 15 also. Right, if I move to moments then, it's where I take the moments from. So where would it be good to take the moments from? Well, I'm trying to find the distance from A. of where the centre of mass is. So I'm going to take moments about A. Now, what moments have I got? I've got this moment, the reaction force of the support C, and that's going to tilt the rod in an anti-clockwise direction. I've got a moment for the centre of mass, which will tilt the rod in a clockwise motion. I've got the reaction force for D, tilting the rod in an anti-clockwise direction, and that is it. So remember, clockwise equals anti-clockwise here because the rod is in equilibrium. So if I take moments about A then, I'll do the anti-clockwise ones first. So it's going to be RC multiplied by 1 plus RD multiplied by, now what's that distance? Well, it did give me AD above, it's 2.5. And then that's going to be equal to the clockwise moment, which is x as the distance and 20 as the force, so 20x. Now I can put in the reactions which I've just found, so it's going to be RC times 1, so 15, plus RD times 2.5, so 5 times 2.5, so I'll just put that there, that was 5. So 5 times 2.5 is going to be 12.5. And then that's going to be equal to 20x. Now if I add those two together, I'll get 27.5 equals 20x. And then divide by 20, x is going to be 1.375. And that means then the distance of the centre of mass from A equals 1.38 metres rounded to 3 significant figures. That is it for the centre of mass. As you can see, hopefully, very similar concepts to the equilibrium part. Now we're going to move on to tilting and have a look at what tilting means. So, when a rigid body is on the point of tilting about a pivot, the reaction at any other support or the tension on any other wire is 0. So this diagram below could be at the point of tilting if that force where the hand is applied. Okay, so let's have a look. So if this force here is applied, then the rigid body will start to pivot. Now, if this actually pivots in a clockwise direction from that force, you can see that very slowly, actually, the rigid body will come off this first support entirely. Okay? So when it's at the point of tilting, it's not in equilibrium anymore. Okay, so the reaction at this support will be 0 because it's actually lifted off the support. Okay, if we do it the other way, if we added a force there, then if it's at the point of tilting, this essentially is happening. So the rigid body is tilting on the first support. So there'll still be a reaction on the first support, but it's not currently on the second support. And that's why the reaction will be 0. So we talk about the point of tilting as it's about to tilt. This actually links to tension as well. So if we've got, say, this suspended by a piece of inextensible string, the reactions will become tensions. And again, the same thing applies. If you think about a necklace, if you pull one side of your necklace and keep that taut, the other side will be slack. Okay, especially if you've got a pendant on the necklace, that could be the weight. Okay, so one side, one tension can be considered as 0. Okay, so if we look at examples of this then, example 1, now it's saying a uniform beam. So AB has mass 45 kilograms, length 16 meters, I think that's what those values add up to there. It rests horizontally on supports C and D, so currently it's in equilibrium. When a child stands at A, the beam is on the point of tilting about C. So point of tilting about C. We've got to find the mass of the child then. So I'm going to add to my diagram. It's a uniform beam, so the weight acts as the midpoint. So I'll put the weight about there. So that's 45G. I'm going to put the child on. So standing at A, not standing in midair there, they're standing at A. I just didn't want to get in the way of the diagram. And they're going to have a mass. Now, I'm thinking about my dimensions here. If that's the midpoint of 16, this is 8, so this will be 3 if I need it. And if this is 8, well, that will be 6 if I need it, okay? Now, if it's at the point of tilting about C, this is where the beam is pivoting around, and that's the pivot point, okay? So actually, like the diagram before, the beam will begin to lift from the support D. So actually, that might as well not exist. Okay, so you're not going to have a reaction at D. So there's going to be no reaction force, or the normal reaction, no reaction force at D. So I will put a reaction force here for the support. So remember, everything's acting on the beam. So we're only interested in the forces acting on the beam. Right, so it's where I go from here. If I'm going to think about taking forces and looking at forces, well, if I resolve upwards, I've got 2 unknowns, okay? R is going to be equal to mg plus 45g. So that's not really helpful at this point. If I go straight onto moments, if I'm taking moments about C, then the reaction at C can be ignored, and then I can just hopefully then work out the maths. So I'm going to look at moments about C. So the first moment I'm looking at is the moment created by the child. So it's going to tilt the beam in an anti-clockwise direction. There's another one here, the centre of mass, so that will tilt the beam in a clockwise direction. So I've just got two things, and remember, if it's resting horizontally at the time being, then clockwise equals anti-clockwise. So I'm going to do the anti-clockwise first. That's going to be mg times by 5, which equals 8. Sorry, it's about C, isn't it? 3 as my meters times by the force, like so. So this is 5 mg, which equals 135 G. If I divide by 5G, I'll get what m is. Stop. So 135 G divided by 5G. M is 27. So therefore the mass of the child has to be 27 kilograms. Example 2. A non-uniform rod, AB, of length 10 meters and weight 40 newtons, is suspended from a pair of light cables. And they're attached at C and D, where AC is 3 meters and BD is 2 meters. When a weight of 25 newtons is hung from A, the rod is on the point of rotating. So find the distance of the centre of mass of the rod from A. Okay, so straight away I don't have a diagram, so I'm going to draw one now. We've got a uniform rod AB. It's got length 10. The weight of it is 40 newtons, but I don't really know where it's going just yet because it's non-uniform, so I'll leave that off for a moment. Suspended from a pair of light cables. Now light is a modelling assumption, and light means that we can treat the cables as having 0 mass, but because we're talking about cables, there's going to be tension involved. So rather than having normal reactions or a reaction force, it's going to be tension instead. So now it's hung from C and D, and AC is 3 meters and BD is 2 meters. So maybe I'm going like that for 3 meters, and then that for 2 meters, and then the middle will be 5 meters. So that's C, that's D, and I'm going to do 2 cables going up with tension, so that's tension at C, and then another cable going up here, that's tension at D. I'm just going to put the weight for the centre of mass about there, okay? And that's what we're trying to find, the distance of the centre of mass of the rod from A. So I'm trying to find this distance here. Now I've added a weight, or someone's added a weight, which is hung from A. So there's going to be a weight here of 25 newtons. I'm just going to add on that length as being 5, that length as being 3, and that length as being 2. And if I need anything else, I can find it. Now, it talks about this point of rotating. So the fact that we've got this weight on A now, this whole rod is going to start rotating. Now, if it starts rotating, the C is going to become the pivot. Okay, it's going to pivot around C. And that means that the cable at D is going to become slack. Okay, and then the tension at D is going to be 0. All right, so you can ignore the tension at D. Now, we don't actually need the tension force or need to find it. Just like the last one, I didn't actually need to find the normal reaction. So if I don't need to find the tension force, then it might be better to take moments about C to then find this distance X, okay? Because then the tension will be ignored. Or you could find tension by just making it equal to 25N plus 40N, because we are in equilibrium for the time being. Okay? So I'm going to try one method. I can always do another method if needs be, but I'm going to look straight away at taking moments about C. So if I've got moments about C, I'll have this moment here, which is an anti-clockwise moment. I'll have this moment here, which is clockwise. And clockwise equals anti-clockwise. So I'm going to say 25 times 3 for the anti-clockwise moment is going to be equal to, now I want this distance here, and this bit here, I want that distance. Now if the total distance is X, it's going to be X minus 3. So I'm going to do it as 40 times X minus 3. And what will I get? Will it be 75 is equal to 40x minus 120? If I add 120 onto this side, I'll get 40x equals 195, and I'll write it this way. If I divide by 40, I'll have x equals 4.875 meters. Okay, so you can find X that way. I've not necessarily took moments about A. Let's see another method for this. Let's see that we had, say we want to get the tension and we want to do moments about A. So I will do forces first. So I'm going to resolve upwards, and I'll have the tension at C. Really the only tension now is going to be 25 plus 40, which is 65 newtons. If I then decide to take moments about A, I will have different things happening. So I'll just get rid of these parts because they'll have changed, or some will have changed. This force of 25 newtons is not going to cause a moment. There's no perpendicular distance, so I'm ignoring that. This will cause a anti-clockwise moment, and then this one will cause a clockwise moment like before. So I'll do the anti-clockwise first. Tension times 3 is equal to x this time, so x times by 40, or 40 times by x. Now this should give us the same value as x before. So I know tension, it's 65, so 65 times by 3 is 195, and that's going to be 40x. And then if I divide by 40, you can see I've already got the same thing as above. It'll be 4.875. So I gave you a few options there just to show you that it's easy to for me to say which one I would do or what we can do, but you can literally just try something first and see if it works. This worked just the same as that one. It was a perfectly fine method. So I'm just going to finish this one off. I'm going to say it's asked for the distance of the centre of mass from the rod A. So the centre of mass from A I should put the distance of the, missed all that out, the distance of the centre of mass from A is 4.88 metres. Alright, I'm going to get you to practice that one yourself. So you've got a partial diagram. I'll read it out. So you've got a uniform plank, so think about what that means. It's got a mass, 100 kilograms, and a length of 10 metres. So you should be able to know what the other length is here. It rests horizontally, so think about what that means for the time being. It's on 2 smooth supports, A and B, and a man is going to stand at the end of the plank. So he's going to walk from one end of the plank to the other end. He's going to start at A and then walk to the other end, and his mass is 80. So we need to find the distance he can walk past B before the plank starts to tip. So he should be supported by the supports A and B, between A and B when he's walking. It's when he gets past B is when the plank should start to tip. Okay, so I'd be drawing the man past B, and think about which support is going to become redundant then if it's at the point of tilting this plank. Alright, see if you can have a go at that question. And then that will be the end of the video.